Hello, I wanted to talk about atomic structure, but beforehand, I wanted to tell you a little bit about where all of these protons and neutrons and electrons even came from. These are slides that I keep editing every year, starting in 2016, and I thought you would find this rather interesting. You won't see my video pop out here on the side in many of these slides because the slides are a little bit busy. But this is more for informational purposes. Near the end of the video, we'll talk in great detail about the models of the atom and actual atomic structure. So, at time equals 0, we've got the hypothesis of the Big Bang theory. What if the universe could be squeezed into the pinhead of a needle? You know, a huge explosion would, of course, occur, and 10 to the minus 24 seconds later, after the Big Bang, you've got a primordial soup. Now, this primordial soup contains things called quarks, gluons, leptons, antileptons, a whole bunch of radiation, and there are rapid collisions and decay because of the density and extremely high temperature. Following that, at a mere 10 to the minus 6 to about 1 second after the Big Bang, quarks begin to come together to form protons and neutrons. And protons and neutrons are the fundamental things we focus on in chemistry that make up the nucleus of an atom, okay? Now, between about 10 to 1,000 seconds, these are when protons and neutrons actually start colliding with each other. Okay, and they are held together by the strong force, okay, the nuclear force or the strong force. All right, now fast forward, I don't know, billions of years later, but 350 BC, okay, we have this philosopher called Aristotle who proposed the elements air, earth, water, fire, and ether, and everybody believed this for about a couple thousand years. Okay, now, the Greek periodic table is kind of shown here, and it has this little parchment paper kind of looking thing. So it's very strange, okay? But that's the periodic table of the ancient Greeks. Now, along came Democritus, all right? Now, he proposed, there's a little statue here partially of him, and in 400 BC he proposed that there are very small particles that could not be destroyed and that make up all matter. But his theory was not accepted, partly because Aristotle refused that, and he was a big guy back then, and everybody kind of liked to go along with Aristotle to be popular and have their ideas accepted. And Democritus was rejected, all right? But he was right. But like I said, people held the wrong belief about what actual atoms are for a couple thousand years until Dalton's law of theory came about, all right? Now, fast forward to 1897, quite a many years ago, the electron was discovered by J.J. Thomson. Okay, he's credited with the discoverer of the electron, and he actually measured the mass to charge ratio, okay? On the top, you have a Crookes tube just under visible light. And then on the bottom, we have the same Crookes tube with the lights turned off. And you can see this glow that's being produced as the electrons are shooting through this vacuum and hitting a fluorescent phosphor on the right. And this is basically how the older television sets operated. Very quickly in succession, atomic theory developed, okay? So just a few years later, we've got Thomson's plum and pudding model of the atom. So J.J. Thomson was the discoverer of the electron, and he decided that the electron should be in the atom, and there it is. The electron are these little blueberries with the negative signs in the middle, okay? And they're all dispersed throughout the atom. Now, it was greatly understood at the time that similar charges repel one another. So a negative electron is going to repel another negative electron and push them away. So what is holding these things in the atom? Well, you've got this ball of positive charge. So it was very nebulous what this orange or salmon-colored material was. but J.J. Thomson knew exactly that atoms must be composed of electrons. They're negatively charged, and that's what all these little blueberries are, okay? Now, a few years later, Rutherford did his now famous gold foil experiment, and I'll show you more about that in a bit. Now, if this was done in the 20th century, we could imagine that Rutherford would take a selfie among his fellow scientists. So this is just a picture of NASA. It's not really the Rutherford Experiment. But I did want to talk much more in greater detail about what Rutherford Experiment was, how he did it, what it showed the atom to be composed of, and also the nuclear model of the atom, and we'll start going from there, okay? I've provided you a couple of links. Hey, back again on the video. I've provided you a couple of links in the description below. You've got this video here that I highly suggest watching, and then you've got this Rutherford Simulation experiment, okay? Now, the first video is going to be a more modern rendition of the Rutherford experiment. So we've got this electronic detector, a radiation source, and a robotically operated stage, and it's an awesome video. I just can't emphasize it enough. Watch this video to see how the Rutherford experiment would be conducted today, like in 2022, all right? Another link that I've provided in the description of the video below is a link to the Rutherford simulation, and I'll now show you a little bit about the PhET website. Okay, they have a lot of different interactive simulations. Check them out. This is the Rutherford scattering experiment. You just click on the play button, and this runs an HTML5 simulation, which runs on iPad, even your phone, any computer you have that runs an internet. Okay, so you can check out the plum and pudding model, and then you can check out the Rutherford atom, okay? So I'm going to click on the Rutherford atom here. I'm going to hit the pause button down on the bottom, and I'm going to demonstrate over here on the left what's happening, okay? So there's this lead shield, okay, that contains a little bit of radium in it with a small hole drilled into it, okay? And alpha particles, we'll talk more about what alpha particles actually are a positively charged atom that shoots out at very high speeds, 80% the speed of light, okay? So this is extremely fast, and it's going to hit a gold foil, okay? Here's the gold foil. And then on the other side, he's got detectors. You've already watched the YouTube video to see how you know, a modern day detector is going to detect, okay? So you can put the detector over here to see if these particles go right through the gold foil film. You can put a detector over here on the left where I'm wiggling my mouse to see if particles hit the gold foil and then are deflected at an angle. And you can even put the detector back over here near the origin source of alpha particles, okay, where I have my mouse wiggling, to see if particles are actually backscattered from the gold foil film, okay? Now, if I click the on button, there's this kind of like flashlight thing, okay, and that's the alpha particles that are impinging on the gold foil, okay? Now, over here on the right, we have a model of, well, I'll just start with this. So this shows a gold atom, a gold atom, a gold atom, and a couple are off the screen here. And these dotted lines represent electron orbits, okay, electron orbits. And if we click the start button, what we're going to see are these particles that are shooting up from the bottom, okay, because that's where they come from. They come from the radioactive source, and then they impinge on this gold foil, okay? Now, since the atom is mostly empty space, many of these particles are going to pass right on by and just go straight on through, all right, straight on through the gold foil film. So if the detector is placed behind the gold foil film, most of the particles just pass right on through the gold foil film as though it's invisible. And the conclusion Rutherford made was that the atom is mostly empty space, okay? Now, these purple dots are alpha particles, which are positively charged atoms. And the conclusion that Rutherford made was that the atoms themselves, the gold atoms themselves, are composed of a very compact positive charge, because if you watch these, you can see, for example, let's take a look at this purple dot here. it's been deflected, okay? So it came nearby this gold atom, and it was deflected because the two positive charges repelled one another, all right? So every once in a while, you have deflection. And if you wait a very long time, you can actually see a direct hit occur, and then one of these purple alpha particles actually backscattered in the backwards direction towards the, I didn't pause it in time, towards the actual radioactive source. And it's completely random. You can run this simulation again and again and again, and sometimes you'll have to wait a very long time. Okay, take a look at this purple dot right here. This is the one that's been backscattered towards the detector. If you watch this purple dot where my mouse is hovering and I click play, you see how it's going backwards? Yeah, so every once in a while you can see one of these purple guys, oh, there's one, make a direct hit on the atom, and then it backscatters, okay? And then using a whole bunch of math to calculate geometry and probability, you can find out how likely that is. Let's take a look at a zoom in of one atom of gold, which contains a whole bunch of positive charge. These alpha particles are positively charged, so most of them just go straight on through without any deflection at all. And this is an extremely close up, okay? So we're basically, every once in a while you get a direct hit, and the positive charge of the gold nucleus, this big huge thing of red and gray, is going to cause the alpha particle, if it happens to make a direct hit on the gold atom, basically backscatter and come back towards the source, okay? So that was the simulation of the actual Rutherford experiment, and it came up with the nuclear model, which I'll explain more in future videos.